All right, let's get started. So we've just given out the exams. Let's have a little bit of housekeeping. So to date, all the grades are up to date on Blackboard, every one of them. So what I mean by that is Exam 1 and Exam 2 is posted. Homeworks 1 through 7 are posted. They're all up there, okay? The attendance grades are up to date. So right now, today, that is your grade in the class. So I know that some of you, what was it, the at-home game, where you start breaking out the Excel sheet and you start goal-seeking, like, what do I need to make on the final to get a D or something like that? So you had engineering computations. You can do goal-seek. All right. So don't forget, there's 2 more homework assignments in the semester. We have homework 8, which is posted. It's due on Monday the 16th. And then on Monday the 16th, I'm going to give you homework 9, and it's going to be due Friday the 27th, and that's the last day of the semester. So that's it in terms of homework assignments. What?
2 weeks left?
What? 3.
Well, that's including the final week, though, right?
No.
Is our exam 3 or 5?
Yes.
Okay.
Yes. So we have this week, we have next week, we have the week after, finals. No. No, we're trucking along. Let me say this. Hold on. Let me say this about the exam, because I really want to be crystal clear about this. The final exam is going to cover development length, and it's going to cover columns and beam columns. That's the exam. However, I don't know how it's happening this semester. We are making excellent progress in terms of course material. We're going to be done with development length. If we're not massively done with it today, we're going to be done with it within the next lecture. And then that's 3 weeks for columns and beam columns. I'm just going to tell you, columns and beam columns do not take 3 weeks. Okay? So let me be crystal clear when I say this. I am not going to add additional material to the final. So everybody take a breath. Everybody take a breath. However, no. No, listen to me.
You're going to test us twice as hard now?
You. Will you give me a second? I'm not going to give you an additional homework assignment either. This is what I was going to say. If you want, there's a lot of stuff we could talk about. We could talk about wall design, foundation design. We could talk about continuous construction. We could look at two-way slabs, slender columns. We're not doing that. Okay. We can talk about that. No, we'll review the stuff maybe that's pertinent to us. No, but listen. What I'm getting at is this. I'm happy to cover additional materials. I'll be honest, I'm probably not going to prep like super nice PowerPoint slides and all that since we're going off script. But I'm happy to talk about some stuff that I think is relevant. Like if you can do a reinforced concrete beam design and you can calculate development length, you can do a retaining wall, because there's really not that much different. The only thing you need to know is a little bit about active and passive pressure, which we can talk about in here. That's not that big of a deal. You can do foundation design if you can do columns and you can do development length. You just need to know a little bit about punching shear and some things we haven't talked about yet. But I do want to let you know that we're going to finish on time, probably a little early, so we're going to have time at the end to talk about some stuff that we haven't talked about in the end. Like continuous construction. That's really important. And so we might have time to discuss that, and I'd kind of like to talk about that as well. It's like, how do you deal with beams that are overhanging, that have positive and negative bending regions? So you've got rebar up top and rebar on the bottom, and you've got development considerations and whatnot. So those are interesting things to consider. We'll talk about that. We'll talk about that near the end, but I want to be absolutely crystal clear. It's not going to be on the exam, and there's not going to be an additional homework assignment. But I'm still taking attendance, so it's on you to come or not. So that's the caveat. Okay. All right. Any questions on the schedule and on bookkeeping between here and the end? All right. Let's get back to development length. That's a good no. That's not why I'm canceling class. I'm glad you brought that up. So we're not having class on Friday because it was a big yellow bubble right there on the slide. I totally forgot to mention it. So yeah, I have a little bit of an exam of my own on Friday, so I'm not going to be here. So yeah. What's that? Yeah, if you wait till the last minute, it only takes a minute. Yeah. But yeah, I'm not going to be here. Let me say this. I'm hesitant about whether or not we do an online lecture or not. I'm actually kind of thinking that we are because I can set the stage for a lot of basic column provisions that we're going to use that will make our lives a little easier when we do column analysis and design. Columns are actually really simple. They're not that hard, especially when you're looking at short column analysis and design versus long column analysis and design. The difference is you've got to account for buckling of long columns. But walk before we can run. Let's take it one step at a time. So, example 16a. We finished this example, right? Okay, so this will be a nice place to pick it up. We're going to do example 16b. This is going to go real quick, okay? It's going to go real quick because if you understood how 16a works, example 16b is going to go a lot faster. There's a couple things I want to point out so that everybody's aware of what's going on. First thing I want to point out, we're looking at the development length for the 4 uncoded longitudinal bars in this cross section. Let me ask you a question. Can anybody tell me right off the bat what's one of the factors that's going to change for this? Just looking at the beam. What's different with the bars here versus the bars here? They're on the top, so our top bar factor is probably going to change, right? Okay, so there's that. We've got some lightweight concrete, and I went ahead and gave you lambda. I want to talk about this bottom bullet real quick because this is kind of important, okay? So what we've got here is some information on the design. So if you recall, we talked about, bless you, we talked about how if you're in design mode, you know how you do the math, like you've got your, MU, you determine MN required, you calculate your required rho, rho BD to get a required area of steel, right? So in this problem, the engineer provided us what was that required area of steel, and it came out to be about 2.88 square inches. And then what happened from there is the engineer took that 2.88 square inches and they went to the rebar charts and they said, okay, I'm going to use 4 number 8s. And if I use 4 number 8s, it has an area of steel of 3.14. So is that enough steel to meet this requirement? Yeah. In fact, it's more, right? Now, the idea behind development length is if this was 3 square inches and this was 6, that is, if I provide double the amount of steel that I need, then I only need half as much development length. Does that make sense? So what we're going to do is we're going to do some calculations, but we're going to reduce this development length based on that ratio. We're going to cut it down some. So you're going to see these development length values are going to slowly start to trickle down a bit because we're able to adjust that. Does that make sense? Okay, let's get into example 16b and let's just go to work. All right. Actually, you know what I'm going to do? This is what I'm going to do. I'm going to, hold on, snipping tool. I'm lazy. So now we've got all the data necessary for the problem. I thought, man, I should have been doing this all semester. Okay, so let's see what's been pointed out to us. Let's talk about material properties. We know that FC prime is 3.5 KSI. We know that our lightweight concrete factor, the aggregate factor, is 0.75. We got 60 KSI steel. We know the differences between how much rebar was necessary and how much was provided. We're going to do it with KTR as 0 and KTR as computed, just so you all see the difference of that, and also accounting for the steel reduction. We've got our beam dimensions here, and you can see we got number 3 stirrups at 8 inches. So let's just take this one step at a time. So the first thing I want to do is ask you this. Let's just say parameters. It's not system parameters. What's that? This is, no. I'm just not writing the word system. All right, let's start off. What is the bar diameter for this problem going to be? What size rebar are we looking at? Number 8. What's the diameter of a number 8? 1 inch, right? Anything that's a number 3 to a number 8, take that number, divide it by 8, and that's the diameter. So if it's a number 7, 7/8 inch diameter. If it's a number 6, it's 6/8, or 3/4. So anything else you can look up. So that's pretty easy. Now, before we handle the top bar factor, let's do the other two. What's the epoxy coating bar factor going to be? 1. Why? These are uncoated bars. So this is 1.0, and I'm going to say uncoated. So let me show you something. Anytime I write these factors, I'm going to say 1.0, and then over here on the right, I'm going to go ahead and put uncoated. In other words, I don't want you to see like, oh, these numbers just came out of nowhere. No, there's the 1, and then there's the reason. Okay. So how about the size factor? What is psi sub s going to be for this problem? Everybody remember, what's the dividing line between what changes your psi sub s value? If it's a number 6 bar, so we're dealing with what? Number, which makes this 1. So, and the reason it's a number 1, or the reason it's 1 is because we're dealing with number 8 bars. Okay. Now, let's talk about that top bar factor. What is the top bar factor for this problem going to be? 1.3. Okay. Now, what determines that specifically? I mean, there's top bars, but there's something else. Yes. Okay, so I'm going to put top bars. But remember, this dimension right here, that dimension from the bottom of that bar to this, has got to be greater than or equal to 12 inches. Now, obviously, I mean, look at your effective depth. It's like 23 inches. So, obviously, that's not a big issue. Sound good? No, remember why that is. It really has nothing to do with loading. It's more about, remember when you're pouring cylinders? Remember back in materials lab, you pour cylinders, and if you don't tamp it, give it the tap on the side, what can you get in that cylinder or in that specimen? You get voids, you get air pockets. And just based off gravity, when you're pouring anything with fresh concrete, it's more likely to get voids on the top than you are the bottom. If you've had the rebar in the bottom, because of all that concrete weight, it's less likely to get as many air pockets and voids. So you're going to get more of a developed connection at the bottom just because of gravity. So it's a good question. Everybody good on that? Yes, yes. But, I mean, look at this. I mean, yeah. Okay, actually, you know what? I'm going to leave that there because I'm going to use these bars over here on the right. So I shouldn't erase that. Okay, now let's look at C sub B. Now remember, when we do C sub B, we're actually looking at the bars up top. So there's 3 distances we need to look at. Now the C sub B is to the center of the bar. Okay? So we've got this distance, which is what? 3 inches. Now how did you get that was 3 inches? It's 26 inches tall with an effective depth of 23. So that's 3 inches. What's that distance? 3 inches. And then what's the other one? All right, it's halfway over to the next one. So it's base, oh, I can do better now. It's that distance right there. Now, how far apart are the bars spaced? 4 inches, that makes that 2. So what I'm getting at C sub B is 2 inches. Does that make sense? Okay. All right. So another thing we'll go ahead and look at right now, note three spaces. There's 4 bars, but there's 3 spaces. Yeah. That's a good point. Now, what is psi t psi e? If I multiply those, what do I get? And what does that have to be less than or equal to? 1.7. So that's less than or equal to 1.7, so that's okay. If it's bigger than 1.7 or equal to 1.7, just use 1.7 in that computation. All right. Okay. So this is just to get everybody's memory banks flowing. So we're going to do this calculation twice. We're going to start off with KTR is 0. Remember, that's KTR is 0 inches, because remember that's in inches. And then we're going to compute. So this is, so let's start off. Let's compute C sub B plus KTR over dB. And that comes out to be what? It's 2 inches plus 0 inches over 1 inch, which is 2 inches. Is that an acceptable value? It is, right? What does it have to be greater or less than? What does it have to be less than or equal to? 2.5. And that's not inches, that's just a value. Okay. So that's that. So now we can go ahead and compute the development length, but we're going to adjust it here in a second. So development length is 3 over 40 Fy over lambda square root of Fc prime, and then psi t, psi e, psi s over that ratio, and then d sub b. So we've got 3. What's Fy? Exactly. It's 60,000 psi. Because that square root of Fc prime on the bottom, that's going to be in psi. So, and then 1.3, 1, 1, and then 1 inch. All right. 40. What's lambda? 0.75. Square root of 3,500 psi. And then the ratio, that's just 2. What does that come out to be? Now, first off, what are the units? Inches, because look what happens. The PSIs cancel, and the only thing you're left with is actually this value right there with units, just the D sub B. 65.92. We'll just call it 65.9. Is that it? Do I have a second on that? All right. Now, this is the part that's new, okay? What I can then do is I can say, all right, let's look at an LD reduced. And so what I can do, and this is another reduction factor that I can apply, is I can take the LD that I just computed and multiply it by the ratio of required steel to provided steel. In other words, I got that 65.9 inches, but this is for a beam that needed 2.88, and I provided 3.14. 60.44, so we'll say 60.4. Do I have a second on that? Everybody good? All right. Sound good? Now we're still getting some numbers that are a little long, so maybe we can try and look at KTR. Let's see what happens if KTR is not 0. What if we compute KTR? Let's see what happens. KTR is not 0. So what is AV? Or how about this? How about this? Let's be consistent. We have the transverse area of reinforcement, which is basically just AV. Now what is that for this problem? It's 0.22. The area of a number 3 is 0.11, but there's 2 of them. So 0.22 square inches. Okay? Now, what is our stirrup spacing? And how many bars do we have per layer? Say it again. Couldn't hear you. 4. Bless you. We're taking the longitudinal bars per layer. 1, 2, 3, 4. So, therefore, KTR is 40 times the transverse reinforcement over S dot N, so 40 times 0.22 square inches over 8 times 4. What does that come out to be? 0.275. Do I have a second on that? And what are the units? Inches.
Quick question, I feel like this should be simple. Where does the stirrup spacing of 8 inches come from?
Yes, just to make a point. Just to make a point. Everybody good? All right, so what's the next thing I need to compute? The ratio. So C sub B plus KTR over dB. What does that come out to be? I'm not going to write it out. I think you all can do that by now. 2.275. Is that acceptable? So just go ahead and tell me, what does the development length come out to be? And then what does the development length reduced come out to be? Because I think once you've got that updated value, I think you're good. I mean, it's a long equation, but honestly, are these development length problems really that hard? I mean, it's really simple. It should be. Okay, so for this one, we'll just call it an even 58, like 58.0 inches, about like that. All right, and the reduced one, 53.1. Do I have a second on that? Okay, so is everybody okay with this? So again, like here would be our raw value of 65.9. We're able to reduce it quite a bit with actually computing KTR and applying a reduction. Now, this right here by itself still doesn't address one of the most fundamental questions about development length is, what if that's still not enough? That's 53 inches of embedment. Maybe that's not. Maybe we need to cut that down a bit. Okay. Now let me say one thing. For retaining wall or for development into a column, this is not good enough. We need to do something else. And I'll show you what to do here in a quick sec. Yes?
So does that, each bar has to be that far?
Yes. Each bar would have to be embedded that far based on these conditions. We can improve upon that, and I'm going to show you real quick and then we'll call it. I know y'all are packing up. Just give me one sec. We can improve upon that by doing this. What happens when we bend the bar? Okay? If you bend the bar, I mean, think about it. Like, imagine embedding that into concrete. Just because of the change of geometry, the fact that you're hooking that bar, you're going to get a significantly stronger bond than if the bar is just straight into the concrete and you're just relying solely on friction between the concrete and the ribs of the rebar. You get a much more developed bond. Now, there's a couple things you need to be aware of. Number one, there's really only two geometries that are allowed for hooks for bending rebar. One is a 90-degree hook. One is a 180-degree hook. It's pretty simple. The geometry, I mean, it's pretty much a lookup. There's basically your limits. And the computation of development length is actually remarkably simpler. And we're going to review this next time. I just want to show you this, okay? Your top bar factor and your size factor are gone. They're gone because they don't really affect the development of a hook. Now, the epoxy coating factor does. That does affect the development of a hook. So that's the same one as before. There is a new one here for cover and confinement. We're going to talk about this next time, but let me say one thing. Development length of hooks, as a rule, do come out smaller. And this can really serve to reduce development length quite a bit. We're going to see some examples here in a little bit where development length was like 50, 60 inches before. It's only like 20 inches now, or maybe even less. So just be aware of that. We got some significant opportunities here. That's all I got for you. See you on Wednesday.